In mechanics and physics, simple harmonic motion is a type of periodic motion or oscillation motion where the restoring force is directly proportional to the displacement and acts in the direction opposite to that of displacement. Simple harmonic motion can serve as a mathematical model for a variety of motions, such as the oscillation of a spring. In addition, other phenomena can be approximated by simple harmonic motion, including the motion of a simple pendulum as well as molecular vibration. Simple harmonic motion is typified by the motion of a mass on a spring when it is subject to the linear elastic restoring force given by Hooke's law. The motion is sinusoidal in time and demonstrates a single resonant frequency. For simple harmonic motion to be an accurate model for a pendulum, the net force on the object at the end of the pendulum must be proportional to the displacement. This is a good approximation when the angle of the swing is small. Simple harmonic motion provides a basis for the characterization of more complicated motions through the techniques of Fourier analysis. Introduction. The motion of a particle moving along a straight line with an acceleration which is always towards a fixed point on the line and whose magnitude is proportional to the distance from the fixed point is called simple harmonic motion. SHM. In the diagram, a simple harmonic oscillator, consisting of a weight attached to one end of a spring, is shown. The other end of the spring is connected to a rigid support such as a wall. If the system is left at rest at the equilibrium position, then there is no net force acting on the mass. However, if the mass is displaced from the equilibrium position, the spring exerts a restoring elastic force that obeys Hooke's law. Mathematically, the restoring force F is given by F equals minus K X. Display style mathbf F equals K mathbf X. Closing curly bracket, where F is the restoring elastic force exerted by the spring. In SI units, N, K is the spring constant, Nm-1, and X is the displacement from the equilibrium position, M. For any simple mechanical harmonic oscillator, when the system is displaced from its equilibrium position, a restoring force that obeys Hooke's law tends to restore the system to equilibrium. Once the mass is displaced from its equilibrium position, it experiences a net restoring force. As a result, it accelerates and starts going back to the equilibrium position. When the mass moves closer to the equilibrium position, the restoring force decreases. At the equilibrium position, the net restoring force vanishes. However, at x equals 0, the mass has momentum because of the acceleration that the restoring force has imparted. Therefore, the mass continues past the equilibrium position, compressing the spring. A net restoring force then slows it down until its velocity reaches 0. Whereupon it is accelerated back to the equilibrium position again. As long as the system has no energy loss, the mass continues to oscillate. Thus simple harmonic motion is a type of periodic motion. Dynamics. In Newtonian mechanics, for one-dimensional simple harmonic motion, the equation of motion, which is a second-order linear ordinary differential equation with constant coefficients, can be obtained by means of Newton's second law and Hooke's law for a mass on a spring. F N E T equals M D 2 X D T 2 equals minus K X. Display style F underscore mathroom net equals M frac mathroom D caret 2 X mathroom D T caret 2 equals KX. Closing curly bracket, where m is the inertial mass of the oscillating body, x is its displacement from the equilibrium, or mean, position, and k is a constant, the spring constant for a mass on a spring. Note that in reality this is in fact an approximation. only valid for speeds that are small compared to the speed of light. Therefore, d2 x dt2 equals minus k m x. Display style frac mathroom d caret 2 x mathroom d t caret 2 equals frac k m x. Closing curly bracket. Solving the differential equation above produces a solution that is a sinusoidal function. X t equals x 0 cos omega t plus v 0 omega sin omega t. Display style x t equals x underscore 0 cos left omega t right plus frac v underscore 0 omega sin left omega t right. Closing curly bracket. This equation can be written in the form x t equals a cos omega t minus phi. Display style x t equals a cos left omega t var phi right. Closing curly bracket. Where omega equals k m a equals c 1 2 plus c 2 2 tan phi equals c 2 c 1. Display style omega equals sqrt frac k m q quad a equals sqrt c underscore 1 caret 2 plus c underscore 2 caret 2 q quad tan var phi equals frac c underscore 2 c underscore 1. Closing curly bracket. In the solution, C1 and C2 are two constants determined by the initial conditions, and the origin is set to be the equilibrium position. Each of these constants carries a physical meaning of the motion. A is the amplitude, maximum displacement from the equilibrium position. Omega equals 2 pi f is the angular frequency, and phi is the phase. Using the techniques of calculus, the velocity and acceleration as a function of time can be found. V t equals d x d t equals minus a omega sin omega t minus phi. Display style v t equals frac mathroom dx mathroom dt equals a omega sin omega t var phi. Closing curly bracket. Speed omega a 2 minus x 2. Display style omega sqrt a caret 2 x caret 2. Maximum speed omega a at equilibrium point a t equals d 2 x d t 2 equals minus a omega 2 cos omega t minus phi. Display style a t equals frac mathroom d caret 2 x mathroom d t caret 2 equals a omega caret 2 cos omega t var phi. Closing curly bracket. Maximum acceleration a omega 2 at extreme points. By definition, if a mass m is under shm, its acceleration is directly proportional to displacement a x equals minus omega 2 x. Display style a x equals omega caret 2 x. Closing curly bracket. Where omega 2 equals k m. Display style omega caret 2 equals frac k m. Since omega equals 2 pi f, f equals 1 2 pi k m. Display style f equals frac 1 2 pi sqrt frac k m. Closing curly bracket. And since t equals 1 f, where t is the time period, t equals 2 pi m k Display style t equals 2 pi sqrt frac m k. Closing curly bracket. These equations demonstrate that the simple harmonic motion is isochronous. The period and frequency are independent of the amplitude and the initial phase of the motion. Energy. Substituting omega-2 with k per meter. The kinetic energy k of the system at time t is k t equals 1, 2, m v 2 t equals 1, 2, m omega 2 a 2 sin 2 omega t plus phi equals 1, 2 k a 2 sin 2 omega t plus phi. Display style k t equals tfrac 1, 2 mv caret 2 t equals tfrac 1, 2 m omega caret 2 a caret 2 sin caret 2 omega t plus var phi equals tfrac 1, 2 car caret 2 sin caret 2 omega t plus var phi. Closing curly bracket. And the potential energy is U t equals 1, 2 k x 2 t equals 1, 2 k a 2 cos 2 omega t plus phi. Display style U t equals tfrac 1, 2 kx caret 2 t equals tfrac 1, 2 car caret 2 cos caret 2 omega t plus var phi. Closing curly bracket. In the absence of friction and other energy loss, the total mechanical energy has a constant value. E equals k plus U equals 1, 2 k a 2. Display style E equals k plus U equals tfrac 1, 2 car caret 2. Closing curly bracket. Examples. The following physical systems are some examples of simple harmonic oscillator. Mass on a spring. A mass m attached to a spring of spring constant k exhibits simple harmonic motion in closed space. The equation for describing the period t equals 2 pi m k. Display style t equals 2 pi sqrt frac m k. Shows the period of oscillation is independent of both the amplitude and gravitational acceleration. The above equation is also valid in the case when an additional constant force is being applied on the mass, i.e., the additional constant force cannot change the period of oscillation. Uniform circular motion. Simple harmonic motion can be considered the one-dimensional projection of uniform circular motion. If an object moves with angular speed omega around a circle of radius r centered at the origin of the xy plane, then its motion along each coordinate is simple harmonic motion with amplitude r and angular frequency omega. Mass of a simple pendulum. In the small angle approximation, the motion of a simple pendulum is approximated by simple harmonic motion. The period of a mass attached to her pendulum of length L with gravitational acceleration g, display style g, is given by t equals 2 pi L g. Display style t equals 2 pi sqrt frac L g. This shows that the period of oscillation is independent of the amplitude and mass of the pendulum, but not of the acceleration due to gravity g. Display style g. Therefore, a pendulum of the same length on the Moon would swing more slowly due to the Moon's lower gravitational field strength, because the value of g, display style g, varies slightly over the surface of the Earth. The time period will vary slightly from place to place and will also vary with height above sea level. This approximation is accurate only for small angles because of the expression for angular Acceleration alpha being proportional to the sine of the displacement angle minus m g l sin theta equals I alpha. Display style mgl sin theta equals I alpha. Closing curly bracket, where I is the moment of inertia. When theta is small, sin theta approximately equals theta, and therefore the expression becomes minus m g l theta equals I alpha. Display style mgl theta equals I alpha, which makes angular acceleration directly proportional to theta, satisfying the definition of simple harmonic motion. Scotch-Yoke. A Scotch-Yoke mechanism can be used to convert between rotational motion and linear reciprocating motion. The linear motion can take various forms depending on the shape of the slot, but the basic yoke with a constant rotation speed produces a linear motion that is simple harmonic in form. See also Newtonian mechanics, small angle approximation, isochronous, uniform circular motion, complex harmonic motion, damping, harmonic oscillator, pendulum, mathematics, circle group, string vibration. Notes. Walker, Joel. 2011. Principles of Physics. 9th ed. Hoboken. N. J. Wiley. ISBN 0-470-56158-0. Thornton, Stephen T. Marion, Jerry B. 2003. Classical Dynamics of Particles and Systems. 5th ed. Brooks Cole. ISBN 0-534-40896-6. John R. Taylor. 2005. Classical Mechanics. University Science Books. ISBN 1-89138922-X. Grant R. Fowles. George L. Cassie Day. 2005. Analytical Mechanics. 7th ed. Thomson Brooks Cole. ISBN 0-534-49492-7. Simple harmonic motion from hyperphysics. Java simulation of spring mass oscillator.